All right, I'm going to record the lecture. So if you have any questions, you can type into the chat, so we can answer at the end. All right, so it's 10 o'clock. So we have 1.5 hours today to go through computational thermodynamics and its applications. So will be few parts, right? We have the fundamentals and the computational, and then we can add the applications too. Okay, I'm going to share my screen. All right, I want to thank everybody for taking this lecture to learn more about thermodynamics. But before we start, you have learned you have taken a few classes already, lectures already this summer about computational material science. So I'm going to talk about computational thermodynamics and its applications. As you know, my name is C CaO, and I've been at Penn State now for 22 years. Still I'm very enjoying teaching my classes and interact with students. Before we start, I want to first go over about usefulness of thermodynamics. I understand that thermodynamics is one of the challenging classes. Some people think it's very abstract and difficult to apply. But I hope at the end of this class, this lecture, and you will start to use thermodynamics for your research, for whatever you do. And first I want to cite this, what Einstein said about thermodynamics, how highly he appreciated thermodynamics. And he wrote, "A law is more impressive, the greater the simplicity of its premises. The more different are the kinds of things it relates. The more different kinds of things, right? All kinds of things actually can relate. And the more extended its range of applicability. It is the only physical theory of universal content, which I'm convinced that within the framework of applicability of its basic concepts will never be overthrown." So that means it captures the essence, the nature what's going on here. And this quote is from this website. And it's also very interesting discussing in the literature about thermodynamics, evolution, and creationists. You know that people are divided by evolution and the creation, but this website is pretty interesting to discuss these different aspects. And also there'll be more kind of reading you can do, and about the thermodynamics. It's very interesting because as you point out here, let me use my set up my point here, over here. I show you by Einstein here. It's range of applicability. Okay, they range to many things. It's more different kinds of things can apply to. But of course, today we are going to talk about thermodynamics materials. All right, so we're going to talk about 4 aspects of thermodynamics today. First, I'm going to give an overview of the fundamentals of thermodynamics. And as many people were told, and many textbooks are written, and they all say, or not all say, most of them say that thermodynamics is for equilibrium only. But I hope after this class, you will realize that that's not true. Thermodynamics is only a very small portion of thermodynamics. And in order to use thermodynamics, we have to do mathematical modeling. So I'm going to introduce a method called CALPHAD modeling. And thermodynamics is mostly related to phase diagrams. Okay? So phase diagrams are usually for equilibrium condition, equilibrium results. But it does show some non-equilibrium too. We can talk about that too. And then after we do the modeling, we have to use them, right? So the material design is one of the major application of CALPHAD-based modeling. So we call it a CALPHAD-based materials design. And as we usually learn that the transport properties, like diffusivity, they are kinetics, right? But I want to show you that they can all be predicted by the thermodynamics. Because thermodynamics itself, it includes non-equilibrium. So that's 4 aspects here. So if you divide by about 90 minutes, 80 minutes, is about the 20 minutes per topic. All right, so let's go over the first law of thermodynamics. I know that many of you, of course, have started this one where you take thermodynamics. Most of you probably have taken twice already. You took at least twice. Some of you maybe 3 times. Your undergrad study, your grad study. Sometimes you have a master degree. So you probably at least twice or 3 times. And this is the law of conservation of energy. But usually when you learn thermodynamics, you only learn first two terms, dq and dw. You don't talk about this term. Why is that? Because whenever people introduce thermodynamics, first law of thermodynamics, they always talk about a closed system, okay? But we know that a closed system is very rare, right? A lot of times it's open system. So you have to add the third term here. This is the mass addition. With UI here, it's the partial energy, partial internal energy of that mass. So that's the first one. And usually we talk about hydrostatic pressure. So we take dW equal to minus PdV. You have minus sign here is because the volume decrease, energy increase for the system. So that's the typical first law you would see mostly with the first 2 terms. I only seen once in the literature, at least maybe not once, a couple of times, very rare. I put this term in 2, okay? But I usually use different symbols, so it's kind of confusing. But remember, this UI is the partial energy, partial internal of that component. This is du to dni derivative without heat, without work. So that's just one of the partial derivatives. All right, so first law, we're done. So we got the second law. Second law of thermodynamics, it says that for an irreversible process inside a system, it has to produce entropy. So that uses the IP here, stands for internal processes. Process, one of them. You can have multi. The entropy production must be positive. So then most of the time we stop here, then we introduce heat. However, if you look at the entropy change of the system, we actually have 3 components. So again, most of the textbook, we start only one term, dq divided by t. We never introduce this term. Very rare you see this term in the literature. And this term is dropped off because at the beginning, we say it's the equilibrium system. Okay, so when these 2 terms are dropped in most of the second law introduction, we introduce the second law, they got 2 big problems. One is introducing chemical potential, because without this term, you cannot introduce chemical potential. Okay, without that term, you cannot talk about non-equilibrium thermodynamics. So that's why in the typical literature, and people talk about equilibrium because that term is 0. Okay, people usually have trouble with chemical potential because they don't use partial entropy to start with. So this is SI here is partial entropy. What it does mean partial? What it does mean? It means ds to dni partial derivative with no heat at equilibrium. Okay, so that's the definition of partial entropy. All right, so that's not. So this is very important because, as I mentioned, if we have this term, yeah, as you will see, the chemical potential is naturally introduced. With this term, we keep the non-equilibrium state. We can talk about all kinds of behaviors, all kinds of transport properties too. So if this is not equilibrium, that means that the dip s is equal to 0 or less than 0. But it's interesting, right? Those are very interesting. If it's less than 0, we should not add here anymore, right? So it's interesting that if it's equal to less than 0, this term should drop. Okay, that's also a little bit confusing because if it's negative, you should put it in there, right? But actually, if it's negative, you should remove it. Okay, when Gibbs did his work in 1800s, and he dropped this term because he was only interested in equilibrium. So that was that means more than, well, more than 100 years now, about 150 years close to, and it's always equilibrium because that term has been always dropped. Okay. So now, now we're going to see the DQ here is connects first law and second law. So we put them back together, we combine law. So first we put a DQ on the left side. And then we define new quantity because this term is kind of tricky, right? What do you mean by the internal entropy production? That means that something happened. Something happened called the internal process. That in the internal process, something's happening, right? Phase transformation, diffusion, heat conduction, whatever. So that's called internal process. That means you have to have a variable to represent it, called internal variable. So the internal variable is taking place. That means it has a driving force. Okay. So now we define a driving force times that the internal process change equal to the energy. Energy is temperature times the entropy production. So temperature times entropy production gives energy. So it's positive heat. Positive heat. Okay. So now you put this back here then you get the combined law. So you put the DQ back into the first law, they got the combined law, which now we have now you have TDS, right? PDV that's still there. Now you have UI minus TSI. Okay, that's TSI here. Because you're mass addition there. And then you have the driving force here. So the combined law becomes like this. And usually you only see, most time, you only see the first two terms after maybe 1/3 of your class. Then suddenly the professor will add another term or say, oh, now I have chemical potential. But now you see that chemical potential is actually defined by the internal energy minus by the partial internal energy minus temperature times partial entropy. So it's a well-defined quantity. That's called chemical potential. And then this term is important because you probably very rare to see in the textbook of thermodynamics because this is for non-equilibrium. So many people have the thermodynamics book, they always say we're equilibrium only because they drop this term to start with. Well, it's of course that's right too because Gibbs dropped it in 1800, right? Now it's also very important that you see for this fundamental equation we derived, and we have these pairs, TS, PV, mu I, Ni, and d xi. So we call them contributor variables. The temperature and the entropy. No minus P here because we have minus some there. So we usually move minus P inside here. PV, minus PV, and mu I, Ni, and minus d xi. Okay, now what you see here is that these red ones we call the potentials. They are homogeneous at equilibrium. And the other ones called molar quantity because they depends on the size of the system. Okay, now equilibrium thermodynamics. So what's the difference then? Well, this is non-equilibrium thermodynamics. We have CAI here. CAI, we use one internal process, but it could be multiple internal processes. Okay, say CAI J. So for non-equilibrium thermodynamics, you must have this term in there. That means the energy is a function of internal state. And the same for the du, that's internal energy. Then for the dg, you just switch the contributor variables. And it is not equilibrium thermodynamics. That means that d xi equals 0. And now you see the xi drops from the function here because it becomes a dependent variable. And that's what we see. That's why as soon as you use these two equations, or use the equation, it's equilibrium thermodynamics. So it's rightly so when people talk about thermodynamics, it's for equilibrium because we only use this term most of the time. But if we want to use the non-equilibrium thermodynamics or the full thermodynamics, we should include d xi here. We should have xi inside our function too. All right, so what is equilibrium then? Like we'll talk about d xi equals 0. Okay, that means there's nothing happening inside the system. No spontaneous internal processes are possible. And but it turned out because there are two variables here, right? Well, two variables, so there are three combinations. The first combination is d equals 0. If d equals 0, you can do derivative, basically. Okay, so we call it smooth equilibrium because you can calculate the derivatives. And another one is sharp equilibrium because d is negative, but d xi is equal to 0 because nothing happens, right? There's no driving force. We call it sharp equilibrium. For example, you burn a wood, it can completely burn, right? Nothing left. Okay, so it's the long equilibrium, a sharp equilibrium because all become carbon dioxide. Another one is that you do have driving force, but the process cannot happen. Okay, we call it constrained equilibrium. That's one we see most of the time in our life, right? For example, the steel we use. So steel is constrained equilibrium because steel should oxidize, right? Aluminum should be oxidized. All the metals, most of them except the gold and the silver, all of them should be oxidized, but they don't. Why not? Because of constraining. Okay? That constrained equilibrium is actually we see the most. We have driving force, but the process doesn't take place. If one example here is that we put it in the big house, for example, you have ice and water, okay? If the ice and water, they coexist, that's equilibrium. That's at 0 degrees Celsius. However, if you go to 10 degrees, then the ice will all be gone, okay? So there's no driving force to form ice, okay? So that's sharp equilibrium because only one state is stable. Another one is that, well, in the refrigerator, you have ice and water, right? What outside the refrigerator, inside, you have ice and water, but you don't connect them, okay? So both are still equilibrium. This is constrained equilibrium, okay? You constrain them. You have many ways to constrain, right? We say the aluminum is not oxidized because we have a scale on alumina. So that's protection. So that's why the internal alumina is not oxidized. Okay, so that means we need to really talk about states of a system and the change of state. That means we need to talk about the equilibrium. We talk about non-equilibrium. Non-equilibrium, we should actually talk about the first derivative, we should talk about the second derivative, and the third derivative. So the G will be a function of temperature, pressure, composition, and the state. So what does it mean? So talk about Gibbs energy, a function of state, right? For example, take water as example again. You have ice, you have water, but that's a minus 10 degree, okay? So now you can see you have a fraction. At the beginning, you have 100% of water, and then time goes, it will change to 100% of ice because ice has low energy. Okay, so you can talk about driving force. You can have differential driving force. So any moment when the water becomes ice, there's a driving force for that. You can calculate. But however, I have a barrier. Right? So then you have to calculate the integral driving force. You have the metastable state of water. You have a stable state of ice. But both of them are stable because the second derivative is positive. So you have driving force. That's called the integral driving force from the beginning to the end. And between the two states, you have a barrier. So in the barrier, you have the unstable range. The second derivative becomes 0. So you see, the energy itself actually covers the metastable, stable, unstable, and the barrier. What is barrier? Barrier is kineticus, right? We think the barrier is kineticus. So transformation barrier actually is free energy. So it's between this maximum point and the local minimum point. That gives you the barrier. So think about this one. If we calculate the Gibbs energy, if we get this function, we can calculate the barrier directly. Then we can talk about how this state vibrate, how it jumps. Then we call it the kinetical coefficient. So we get all the kinetical from this free energy. That's what we're going to mention today too, how that works. Okay, internal variable, as we mentioned, it could be, what does it mean? Basically, anything inside, it could be internal variable. For example, I will talk about the water and ice. So the molecule in the ice state, in the water state, that's internal variable. Or you can talk about the entropy, two parts of entropy, and the ice entropy and the water entropy, they're different. And the volume is different, okay? Ice and volume have different volume. They have different mass, so you can transport the mass. And if you talk about our materials with an ordering, or we can fix fraction, right? Because when the water becomes ice, it takes time. You can take the fraction of the water as the internal variable. So anything internally determines the state is internal variable. So it's very, very broad, very, very broad. Okay, so we talk about the pressure, right? We talk about the pressure, but we know that. So we're not only working on the pressure, we look at the strain, right? For solid state, we have strain. We have electric field, we have magnetic field. They all contribute to our energy. So you can write internal energy now instead of TDS, but we can write the stress, strain, and the electric field, electric displacement, and the magnetic field, magnetic displacement. Then you have the components. You can actually component, as we were mentioning in the future in this class, that you can take electron. Electron is one of the component, right? If you put electric field. And this is driving force. So now, but most of the time, we do not control the electric displacement. We control the electric field or magnetic field, right? Or you control the stress. So then you do a conversion. That's the Lagrange transformation, like we did for Gibbs energy. But you can transform all of them, define another free energy phi. They can do d phi. So d phi now is SDT, and it was now this all change sign. You got this stress, electric field, and magnetic field, and this. But we keep this one because we usually control mass of the system. Then have driving force for internal process. So this is one, of course, most useful to us because those the natural variables of phi are what we control in experiments. So now you can see that now we see the phi for all of this uniform differential. We got the first derivative, right? First derivative, then we do second derivative. So we make a table here. Okay. So the yellow ones are the natural variables. That means after d, the differential quantity, that's independent variable. Then the conjugate variable is in front of the differential is here. Okay. And then this guy somewhere. Oh, this guy is. I can't get rid of this guy. Do you guys see a screen here? This guy. Okay. All right. So for example, the phi to t derivative gives entropy, right? So this is the first derivative. Then if you do the t derivative again, it gives heat capacity. So the inside here is the second derivative. Okay, second derivative. So second derivative, I choose three color here. The first color is red color. That's the diagonal term. That's the second derivative to the same conjugated, same variable. So the t derivative, second derivative, to stress, second derivative, to electric field, second derivative, to magnetic field, second derivative, and to the moles, second derivative. So this quantity, red ones, they're all positive in a system, in a stable system. And the black ones is to the cross second derivative. For example, this one is that you do the temperature derivative first, the entropy, then you do the stress derivative. Okay. Now we know that from Maxwell relations, they are symmetric. You can change order, doesn't matter. Second derivative, because this is fundamental equation. But this second derivative of diagonal second derivatives, they can be either positive or negative. Okay, they don't have to be positive. Some people sometimes we got surprised. Why is that? That's because our laws did not say that has to be positive. And then the last quantity I want to mention is this is the yellow one. Okay. So most of this quantity we have here is between, this one is the molar quantity to temperature derivative, to the potential. But this one is the potential to potential. Okay. We know the potential is driving force for anything to happen. So potential to potential, that's cross term. That's cross term. For example, we're going to show one thing. So this one is thermal transport. It's also Seebeck coefficient. And however, this one, on the other hand, this one is equal to that one, right? Because symmetric. It's symmetric. Okay. So that means this Seebeck coefficient is actually partial entropy. That's also very interesting because some of the quantities are very difficult to measure. Some quantities are very difficult. Some quantities are very easy to measure. Some quantities are very easy to calculate. This matrix gives us the opportunity. For example, some expansion is very difficult to calculate, but very easy to measure. But entropy is easier to calculate. You can measure some expansion and calculate entropy to pressure derivative, and also give you some expansion. All right, so there are lots of interesting derivatives. For example, you can talk about all kinds of potential to potential derivatives. And that's what I will show. One example in this lecture is the Seebeck coefficient. Seebeck coefficient basically is the electron potential to temperature derivative, which is the minus entropy to the electron molar electron, common electron volume, number of most electrons, and there's a partial electron, partial entropy. All right, so I give one example about the internal variable. For example, we're talking about the BCC solution between copper and iron. We know copper is FCC, but however, you must have a BCC copper. You ought to mix it into the BCC lattice. Okay, so that means that the state does not exist by copper itself. But when copper stays with iron, it forms BCC. Okay, so you have to get the energy here, right? You have to get the energy of BCC would be with respect to its FCC stable structure. And of course, we talk about if you work on the nickel-based superalloy, it is ordering, right? Nickel aluminum ordering. So ordering could be another internal variable. And you have a polarization, magnetic spin, electric dipole configuration, and you have defects. They're all internal variables. Vacancy, dislocation, twin, stack and forth, green boundaries, phase interface surfaces. They're all internal variables. Now you can see that you can use thermodynamics to cover all those kind of internal structures. I will show a couple of examples, and we worked on all of them as the different topics: vacancy, dislocation, twins, stack and forth, green boundaries, and so forth. All right, so to do that, we have to do the modeling. We need to get the function, right? We need to get the function of a phase, individual phase, as function of temperature, pressure, and the composition and the configuration, the internal variable. So we use this method called the CALPHAD method. And for example, as I mentioned, the BCC copper. You need to model BCC copper. Okay, that's the internal variable. The CALPHAD stands for calculation of phase diagram, and it has a community. It has a CALPHAD website. It has a journal, has a conference, and it has a foundation. And it has tools too. So today in the afternoon, and Brandon and Adam can show you ThermoCalc, because that's one we use the most. Is because I graduated from that group in Sweden. FactSage is from Canada. Computational is from University of Wisconsin-Madison, where I spent my postdoc research associate there. GMAT Pro is from UK. MetaCalc is from Austria. So these are commercial ones. And if you go to industry, most of the materials companies, if you do the metal side, alloy side, you do ThermoCalc. If you do the chemical side, you have FactSage. And the Computational is with a new company also for metals. And this is for the properties, and this is for the kinetic process. And also you have open source ones too. OpenCalPHAD, that one started a few years ago by one of the developer of ThermoCalc, because he wanted to have open source. And then the PackCalPHAD aspects from our group at Penn State. We started about this one 10 years ago. And now we have a pretty nice tool used to. Okay, I want to mention you about the impact of the CALPHAD. And many of you probably heard about ICME, Integrated Computational Material Engineering. And it was a report published in 2008. Inside that report, it cited CALPHAD software is arguably the most important and purpose-only generic tool available for ICME practitioners. And you probably also know that 10 years ago, about 10 years ago, the United States started the Material Genome Initiative in 2011. And again, is to foster the computational capabilities and data management and so forth. And there's one paper about talk about this material genomics, is from CALPHAD to flight. I'm going to mention their work a little bit in this presentation too. So the process is that you can do the Gibbs energy of individual phases, as because we are mostly working on the temperature pressure composition instead of the electric materials. For oxides, for the ferroelectrics, of course, you want to do the electrical field and also the strain instead of pressure. And to do that, you need the derivatives. We'll talk about the derivatives, first and second derivatives of the Gibbs energy, and which give a heat capacity, entropy, and activities. Then we also need the phase boundary and the phase equilibrium data. So this is for single phase. This is for two or more phases. And then you get the energy. You start with one pure elements. You do the binary, you do the ternary, you do the multi-component. And today, the commercial database, some of them have 20 or 30 elements for this highly alloyed materials like nickel-based superalloy and steels, aluminum, and manganese, titanium alloys. So as soon as I get a database, you can do the material design. You can do equilibrium calculation. You can talk about the lifetime. For example, how long it takes for that determinant phase to form. You have driving force. You can calculate the properties of first and second derivatives of the energy function. And then you need a model, right? You need a model. Okay, so we use a model called computational energy formalism. It's basically sublattice model based on the lattice and the atomic configurations. And you need data. You need equilibrium data and non-equilibrium data. And then talk about phase stability. You talk about stable, metastable, and unstable. You can do all kinds of configurations. Then you can do the different properties. Thermal properties. You can do mechanical properties, electrical, magnetic, chemical properties, transport properties. Actually, last year we started working on information because information is represented by entropy. And then in your tool, okay? So I'm going to mention, depends on how much time I have, I'm going to also mention a little bit about the tools we're developing. And maybe some of you will be interested to work with us to develop new tools. Okay, so models. So model is the key, right? Without good models, it's not going to work well. So sublattice model is based on lattice atomic configuration, as I mentioned. So you have long range ordering that give you the different weak positions. And you have short range ordering as because of the atomic interactions. So you need to have both taking the long range ordering and the short range ordering into account. And you have defects. The defects really determines our properties, right? So we have the way to get the defects into the model. And you have the vacancy, anti-side, and then you have dislocations. So this kind of thing has to be taken into account so we can make use of the computational thermodynamics more. So input data, let's talk about input data, equilibrium and non-equilibrium. So of course, most time you do experiments. So experiments that we typically do is close to equilibrium, or at least to metastable equilibrium. Right? It has all the contribution we have, put them together, you get results. Usually it takes a long time, weeks to months to get your data, because equilibrium takes time. And there's another way to get the data is do the first principle calculations based on quantum mechanics. I think it's the first or second lectures of these short courses. Some of you have taken the quantum mechanics by Professor Dabo. So that's you can do the stable, you can do metastable, and you don't actually do all the contributions because you isolate. You take ideal case, so your calculations are ideal. So you take individual contributions. You take electronic contribution alone, you take a phonon contribution, or you take a magnetic alone, or you take electric alone. So in that case, you can do stable, metastable, or you do the whatever configuration you can think about. And you can talk about all kinds of individual interactions because you can separate all the interactions. So that takes days to weeks. Well, it's substantial improvement, right? I mean, of course, for theoretic calculation, you always have to do experiments to validate it. But the idea is that you can do fewer experiments, do well-designed experiments. And then another one is even faster is machine learning. Okay, machine learning is that you build on your model, machine learning model from the experiment and the DFT data. And it builds the model takes time, about the same time as the DFT time, days to weeks. But however, as soon as you build up the model, like you build a machine, like you build up the calorimetry, like you build up your calculation, then it takes very fast. It takes a very short time, seconds to hours. So you see that we need all of them, okay? We need all of them, right? But the idea would be that you want to start with this one, right? If you don't have enough data, you take some more data set, or you do some more calculations, or you do some experiments. So the idea is that if you combine all this together, they will be very efficiently to generate data for the modeling. Okay, then now we get the data, we went to the calculation phase diagrams, right? So of course, we all know that we have some phase diagrams, but what type of phase diagram? We actually have a variety of phase diagrams. We're going to show some of them here. So you have potential phase diagram. That means all the axes are potentials. The usual one we see is the PT diagram. Okay, that's one we usually see. Another one is for the PT diagram, you can use the combined law, use the Gibbs phase rule. I'm going to use one here, maybe. Okay, so you have then you can change one of the potential to molar quantity, like you can change the pressure to volume, then you can mix the phase diagram. And if you change all the molar quantities, all the potential to molar quantities, then you get molar phase diagram. Then for the molar phase diagram, you can use phase boundary rule. But it's important the Gibbs phase rule cannot be applied for these two diagrams. Okay, because Gibbs phase rule is for the potentials only. Okay, then you can do it because now the multi-component the diagram has too many axes, right? You cannot see them. So you cut it, you section them. So you can section along the potential. For example, isothermal section you have learned before. That's section through temperature. Isobaric is section through the pressure. Or you can a section along molar quantity. Then you get isopleths. That's important. Tie lines are not in the plane in the section because you cut tie lines off. So that means you cannot cut phase fractions use the isopleths. But sometimes you can cut such so nicely, you can still look at the binary phase diagram. We call it quasi-binary or quasi-ternary phase diagram. That's very common in oxide system. In that case, all the tie lines are still in the section. You cut it along the tie line. So of course, cut along the tie line is the same as cut along potentials, right? Because the tie line represented by chemical potential, that means you fix chemical potential. So it goes back to this a cut through sections through the potentials. And another diagram we're talking about Liquidus projection. So that's not a typical phase diagram. There's not a section, so it's projected through the along the temperature, so you can see the phase formation from the liquid phase. All right, so we're gonna now we have 40 minutes. We're now in the 40 minutes now, so we're going to go through some examples. Talk about the different systems. Talk about the pure elements. Talk about the binary, ternary, quasi-binary, quasi-ternary, and the multi-component systems. So we take the iron as example. Of the iron system has been modeled many, many times. The last time it was modeled was 2005. Bu Suman, who is the developer of ThermoCalc and also the developer of OpenCalPHAD. And Martin Selby and Xiaogang Lu, they revised the iron modeling to put the volume, have a better volume model for 2005, that's reference. So in the iron, we typically have FCC, BCC, and the liquid and the gas phase. However, at high pressure, you have HCP phase. And also we know the BC is the magnetic, so you can make contributions. So this is typical model. The energy of a phase is a function of temperature and pressure. So you have temperature component here. They have the temperature pressure with magnetic contribution. You have temperature pressure due to the volume expansion. That's function of pressure, okay? So now I see, I'm gonna show this values in a minute. And then this one is magnetic contribution, because magnetic is entropy. The magnetic spin entropy is log there. This beta is a magnetic moment, Bohr moment. This tau is a critical temperature. And then you have this complex equation for the volume, PV term, gives the energy V to dP to integration. So this is the analytic equation for that. So you have to fit the models, right? Okay, so now we're going to first show you the first term, TMT, is in the function TDB file. I'm going to show that file to you here. So this is the TDB file. So it has this is a text file. So it has a lot of functions. Has function temperature. There's 3 functions defined here. So this gas phase, for example, gas phase, in the gas you have iron and iron 2 molecules in iron. In the gas phase, you have the free energy is F10105T. They have 1005, this one. This function here. These are different temperature intervals. Okay. And so this for the gas phase have 2 species. The liquid is only 1 species. So you have there's one free energy plus a 2 terms. So that one is for the solid phase. So then you have the FCC phase, a BCC phase. You have the BCC energy. You have the magnetic contribution. You have the FCC phase has a magnetic contribution. You have the HCB phase, high temperature BCC has also a magnetic contribution. Then the reference here. So you see that, for example, let's look at the function, the BCC phase. The BCC phase is the low temperature one, so is F10092. So F00192, let's make it a bit larger here. So this is the function we have. So you see, from the low temperature stable one, from room temperature to 1184, that is transformed to FCC. You have one function. Above the transient temperature, it becomes metastable. You have another function. Then above melting, you have another function. Okay, so you get different range because it behaves differently at different range. Some places you have no data, so you have to do the estimation. All right, so that's for the first term. Okay, it's first term. Then for the volume term, they had this 4 parameters: V0, VA, VK, VC. For each phase, V0, VA, VC, VK have function temperature. So this parameters are in the equation we had before. Okay, are in those parameters here. So now you've got the BCC, FCC, HCB, and liquid. Now you got a 4 free energy function. Gas phase is not here because with the gas is not stable. It is high pressure. Oh, you actually stable. You have vapor pressure there. You can calculate vapor pressure, and then you can calculate phase diagram. So this is the potential phase diagram of ion. It's the pressure and temperature. At the low pressure, we have the BCC goes to FCC, then become BCC again, then become liquid. There's 2 pieces that are same structure, but one is magnetic, one is non-magnetic. Then you get high pressure, you get HCP phase. So people believe in the core of Earth is actually HCP ion because of high pressure there. So you got the phase diagram. Now you can apply Gibbs phase on this one. But now you see pressure has volume. Okay, it's a conjugate variable. Temperature, entropy is a conjugate variable. So you can change. So you can get another diagram. You can change one of them, you can change 2 of them. You can change both. So that's your phase diagram, the molar phase diagram of ion. So the pressure goes to volume. Of course, pressure goes up, volume goes down, right? So this is a high pressure, this is low pressure. Oh, this is low pressure, this is high pressure. This is high pressure. And then you have here is that now you have the tie line, because now you have 2-phase equilibrium. Now you have tie triangles, 3-phase equilibrium. And of course, interesting that you see these two lines actually connect together. So this is what here is, these two can connect together, okay? These two can connect together. So it's BCC phase. So this is FCC. So HCP, or the BCC, is BCC here, okay? HCP, FCC, liquid. So it's a molar phase diagram. To change from this to that, it's just the 2-stroke of in the computer code. You can change the axis from temperature to entropy, change it from pressure to volume. Then you replot this diagram because the calculation is done already. And so that's one component system. So let's go to binary. We'll take iron carbon, we'll have iron, not iron chromium. Again, iron chromium has been modeled many times. Many times. Because we continue to gain new knowledge, better model. And this one's done in 2018. I know that Brandy in my group is finishing another one, the newest one. Will be 2020 then. So this one you have solution phase, you have liquid FCC, BC, and you have another phase, sigma phase. That's a very complex phase, okay? You have gas phase, of course. You have misfit gap in the BC phase. You have magnetic contributions in the BCC and the FCC. So now because you have solution, right? You form 2 phases, you have 2 elements mixed, you get a solution phase now. So solution phase, now you have 3 components. You have the reference one, you have the ideal solution, you have the non-ideal solution. So now the solution can be one sublattice, it means all mixed together, like iron chromium in FCC or in liquid. Right? So in that case, now you can just add the elements contribution, you have ideal entropy into the excess term. So you need probably less stability. For this case, I should show chromium here. Sorry, I should change to chromium. chromium FCC. Chromium is BCC. Let me change it now so I never not forget. Let me change this to chromium. Okay, so I have a chromium here. So we need a chromium FCC energy because FCC ion, you have FCC ion there. And then we have the exotherm. Exotherm, we talk about the two-element interaction, right? So this is for the multi-component. I had the equation, but there's two elements. You have ion and chromium interaction. Then you can have zero order, first order, second order. We call it regular solution and the sub-regular solutions. So these are the model parameters. They need to evaluate these parameters. This is one parameter, this is another parameter. Oh, this actually has more than one parameters. And however, for the phases with more than one sublattice, for example, sigma phase, sigma has 5 sublattices, okay? 5 distinct weak positions. So it's a pretty complex structure. So in that case, you have to do the 5 sublattice. They have this 5 sublattice entropy. They have 5 sublattice interactions. So that now becomes much more complex. So that's why sigma phase has been always modeled by 3 sublattices instead of 5 sublattices. So it's become too complicated. You have no data because when you experiment, it measures the combination. It doesn't measure individual sublattice. And so until DFT becomes available, DFT calculation becomes available, we can do complex systems. And again, that's your database for the iron chromium. Okay, so now we still have these functions, right? We talked about it before. Now we talk about the BC phase. Now we have iron, chromium mix each other. So I have chromium, iron, okay? Where's my iron chromium mixing? Oh, here it is, okay? Chromium iron mixture, right? Remember we have zero order, first order, second order. Because the BC mixing is very complex. It causes a whole range there. And then we have magnetic mixing. FCC, same thing, I have chromium iron, we have chromium, we have iron, then I have chromium iron interaction, 0, 1, 2. Okay, and so forth. Liquid is one sublattice. Let's look at sigma phase. Sigma phase, this model, this paper 2018, only considers 3 sublattices, 10, 4, 16 sites. So they have each side has one end member, one element as the end member. Then you have they have no interaction here. You have interaction here, you have chromium ion interaction. Okay, this one. They have some interaction, you have some end members. End member is one element in one sublattice. So now you've got all the phases ready, right? All the free energy, all of them, all these parameters. And then you can calculate phase diagram. This is one we typically see, right? Temperature composition. So temperature composition is a mixed phase diagram. Remember, this is the potential. This is the molar quantity, right? The mole fraction. So now, how does it look like if we change this one to its conjugate variable? That's chemical potential, right? If we change the temperature and the chemical potential, then we see a potential phase diagram. That's how it looks like. So this is the temperature. This is the chemical potential chromium. Of course, the potential never goes to 0, right? Because it's log of 0 is minus infinite. So you see, it goes to infinite when it's pure ion. Its chemical potential is infinite. So now you see that. Now can they apply Gibbs phase rule here? Can Gibbs phase rule here? You can use the areas in single phase, lines are 2 phases, and then you have this invariant reaction is 1 point here. So you got a potential phase diagram. And you can use all the rules we have, the Clausius-Clamp equation, and so forth. All right, so the binary system. Now take a quasi-binary system, calcium and silica. So we actually, it's a ternary system, right? Where calcium, oxygen, silicon. But however, if you cut through calcium and silica line, then you actually get it looks like a binary. because on that section, the oxygen partial pressure is fixed. So it's like a section square potential. That means you keep phase just decreased by 1, so it behaves like a binary system. But however, now we have an issue is that the calcium and oxygen, they are charged species, right? So you have the ionic liquid and the ionic solid phase. So this is for the liquid model. You have calcium, ions, you have silicon, but silicon does not exist by itself, right? Silicon is an oxygen species. And you also have neutral species too. And because liquid is not like solid, so your sublet size are changing, P and Q are changing. Okay? But now your fringe looks like this for liquid. You have this 1, 2, 3, 4. You have 4 of the end members. It means one species in each sublattice. The calcium is the first one, calcium is the second one, calcium is and so forth. Okay. And then you have the entropy mixing in the second sublattice. They have an excess term. So now if you do the model, of course, it becomes very complex now. Now it's a little bit complex, but the sigma phase is more complex. And you see that in 1990, they could not decide which model is better. They have 2 models here. And in 1991, they remodeled it, same group. It's actually my professor, Marcelo. And they changed the Rankine phase. Because they found it should do better. Actually, they changed all the phases, these 3 phases. They all changed because they found they need to improve it. They're just 1 year apart. So you see, you can, this model is like this, right? You gain new knowledge, you revise your model. This is the iteration process. The phase diagram calculate. So this diagram, even though it's a section from ternary system, but it looks like a binary. You can apply keep phase through, but it's binary system too. That's why we call it quasi-binary. It's not a real binary, it's quasi-binary. It's a section, it's isopleth, but this aspect is so special. It behaves like a binary system. Okay, now let's go to ternary. Again, same equation. Same equation. We have the reference one. We have the ideal entropy. We have the excess entropy. Now, reference becomes more complex now because you have so many different sublattices, right? The equation becomes a little bit complex. You have to talk about all the sublattice configurations. Then you have the mixing in all sublattices. Then you have the interaction in all sublattices. Okay, so this is the ternary interaction term here. You have the binaries, ternaries, okay? And then you could have the complex ternary interactions or even quaternary interactions too. So I'm going to take one example. This was my first modeling back in 1995 when I was in Sweden. I got a visitor, Professor Zhang from China, and he wanted modeling. So we worked together, did the cobalt ion gadolinium system with Busuma. Busuma mentioned to you is that he's the developer of a thermocalc, and when he was a grad student, and he now developed open CALPHAD. So there's a paper there. So now, in terms of liquid projection first, right? So usually when you talk about liquid projection, you project to the composition triangle. So you have a temperature project to the composition. So you get the cobalt composition, gadolinium composition ions here. So you see there's a BCC phase region, FCC phase region, and different compounds, and the BCC ICP there. Okay. So you see this kind of liquid projection. However, this one is only give out the phase region, so it's very difficult for us to see temperature. Okay. But however, remember that it's a projection, right? So I can project to temperature side. So instead of projecting the composition, I can project to temperature. So you now see I project temperature, now project one composition, basically I'm looking from this direction. I look from this direction with temperature on the y-axis. Now I see a different picture here, right? If you see a very different picture. Okay, now I can see exact temperature here. For example, this is eutectic temperature. There's another eutectic temperature, and you have a maximum here. Okay, so this gives you different information. You get the invariant transformations, you get the temperatures, you get so you combine the 2 together, you can figure out what is temperature and the composition from this diagram, right? So this one, see both of them. Okay, so this liquid projection. Of course, then we also have the isothermal section. Okay, so this is fixed temperature, it comes to temperature, you got different phases, you see this compound, they cross the whole range at this temperature. The three compounds. These compounds are very important for the magnetic applications. Gadolinium. And then you can do the isopleth. Isopleth means a fixed composition, right? A fixed composition. and you plot temperature as function component. You fix one component. So what we're going to show is I'm going to show plot this line for this compound, 17.2. I plot on this line, exactly on this line. However, you see, exactly on this line actually completes either side numerically. So it's actually, if you go either side, it'll be a bit different. So this shows that one. So this is along that 17.2 compound line here. Okay. So I'm plotted on the other side a little bit. So you see it's M23. Okay. And you see M3. Okay. You see M7, right? So I'm plotting a little bit to the other side numerically. So you see different. If I plot on the other side, it would be different. Okay. But this way, so this you can see that it gives you the feature that, okay, for example, if you want to make this alloy, and this composition, you have to make sure you heat treatment at high temperature and then quench it down. If you do low temperature, you're going to form different phases. Because they give you the process in design. Okay, I'm going to talk about a quasi-ternary system. Right, so that's cassia, and we talk about a cassia silica, right? So we add alumina into it. So again, it's by Marcellus. Again, he's a professor in our department, and he published his cassia silica paper too in 1990. This is 2006. That's 15 years, huh? 16 years later, the ternary system. And again, you have ionic model, you have the parameters and the invariant reaction. Of course, now become more complicated than the binary system. But you still have the three major terms. You have the energy has the end members, okay, end members, and you have the entropy, you have the interaction, okay, you have the neutrality. And now this is for the liquid equation, for energy access for liquid, so for liquid phase ternary system. And then you can use the parameters. That's only for liquid parameters. At the liquid phase, with the aluminum cast in the first sublattice, with a 1, 2, 3, 4 a species in the second sublattice, you have 2 times 4, 8. So I have 8 end members, right? So you get all the energy of all of them. They have interactions. So these are the parameters they have. And then from that one, you calculate the invariant reactions in the liquid projection. You see all the invariant reactions. You can calculate them, then compare with the experiment. I sort of have experiments. Oh, yes, right. In the parentheses is the experiment value. And the calculated value there. That's what we need to compare with. And it calculates the projection. Okay, this liquid projection is a bit more complicated. You need to put the isotherms on. So these lines are the isotherm. That's what you typically see when you're from the oxide phase diagrams. So this is 1900, 1800, 1700, 1600, and so forth. And another very important diagram is called the isoactivity diagram. For example, at a certain temperature, you do the treatment, right? You want to know how much cassia you should add into it. So you can do that, or you can calculate the diagram. It's called the isoactivity diagram. So this is 1600 degrees C. This is isothermal. You can calculate, say, for the isoactivity of cassia. If the cassia is 0.1, so that's the line here, okay? In order to keep cassia activity at 0.1, you have to balance the alumina and the silica on this line, okay? And also it's very important to see, right? This is like 70% or 70% of cassia, but activity is only 0.1. So the activity of cassia is way off compared to its composition, more fraction, right? Okay, that's why you have very, very strong interaction in the system. Okay, very strong interaction in the system. So that's important for the processing control. Okay, multi-component system. Multi-component system. This is one work I did with ExxonMobil back 15 years ago, no, 16 years ago now. Is for the super hard steel. Is that you can see that is 1, 2, 3, 4, 5, the 5-component system. Of course, you can calculate as many components you want. 20, actually do 20 elements now for the iron database. Yeah. This one's interesting. I did this one is that this isopleth. It's multi-component system. The only way we can visualize them is isopleth. So I fix nitrogen content, fix niobium content, fix titanium content, and the temperature as a function of carbon. So that's a multi-dimensional section with fixed compositions. And then you can see that you have liquid, you have different phases, right? And you can partially apply the phase boundary rule for it. The interesting here is that we see 3 phase miscibility gap. We have 3 FCC phases. So we have regular FCC phase, that's the disordered FCC. We have at high temperature, this one is this one is titanium nitride. Okay, titanium nitride precipitates from the liquid phase. And then the low temperature, you have niobium carbide. So 3 FCC phase coexist in the structure. And also very important, right? You want to avoid formation of the FCC2 at high temperature or from the liquid because it becomes very coarse. Okay, so that means you want to see where you can avoid it, right? You can avoid this phase to form from the liquid phase. So you can see that you want to go to low carbon here, right? If you go carbon here, you get in trouble. The carbon has to be lower, okay? And the lowest one could be, you have to actually go here. Because in this range, you always form some kind of titanium nitride from the liquid. Okay, so you have to control your carbon below this temperature, below this composition, so you can avoid formation of the titanium nitride from the liquid phase. Actually, that was a project we did with Axon. Control, of course, our alloys were complicated because you can change nickel and niobium and so forth, but they don't want us to report all the secret of the elements, so we take a simple one. And now you get basically the shell simulation. And I know some of you work on the additive manufacturing. Additive manufacturing have very fast cooling. So shell simulation is very important because the shell simulation means that the diffusion in the liquid is very fast. It's actually infinitely fast, but in solid very zero. It's very small. So in that case, you can differentiate it from the shell simulation. This diagram shows for a simple system for the solder. Okay, for the solder, this is the dashed line is the equilibrium calculation, and the solid line are the shell simulation. You can see the temperature difference, right? Temperature by about 10 degree difference, okay, for the melting. So that's actually also important too, the final solid temperature too. And I want to show one data, which actually is Brandon's work, and they calculated for the gradient alloy in the additive manufacturing. So you have Yingba alloy here with iron nickel based, and then you have the titanium Ti6 for pure titanium here, the gradient here. Okay, so you can see you can see the microstructures, phases. You can calculate the shell simulation and see what the phase is forming. So now this is in reality is more than 3 components, right? But you can use 3 components to the illustration. So that's the liquid projection. So you see the iron, nickel, titanium liquid projection. And it turned out it depends from titanium to Yingba here. Okay, see on the path here, you do different shell simulation with different phases. Even in the same region here, right? Same region here, you can get the same phase. But in this region, depending on where you are, you can go different phases, different paths. If in this region, you're gonna end up there. This region, you end up here. And in this region, you end up there. So this can give you design. So some place you want to avoid, some place you want to promote. All right, so that's all about computational thermodynamics. Now it's 1 hour. I don't know whether I should ask do you have any questions you want to ask now before we go to applications? Okay, so I guess I probably just continue. And so it's a material design. Application is mainly for material design. So what do I mean by material design? So if you look at a material, we talk about its performance. Performance consists of a set of properties. Okay, then the properties are dictated by the microstructure and the structure. And then how we make the material, what elements to put in there. So most of the research we do, we talk about the process-structure relations. Or if you work on the property side, you talk about the structure-property relationships. So that's the interfaces here. So material design is basically design the things we can control. What can we control? We can control chemistry. We can control the process. So anything else is our measurements. So we don't control them anymore. So that means you can design a lot of things, right? You can design the process. You can design the chemistry. So you can fix chemistry, design the process. or you can fix the process design chemistry, or you put them together, both. So I'm going to show some examples here, and talk about the design which we did. Of course, I showed this one already. Of course, we don't have time to show all of them. I have like 15 minutes to 25 minutes to go over all of them. So when we get a material, that's commercial material, what do we get? We got a called a materials property data sheet. So that data sheet specifies a few things. It specifies the chemistry, tell you what chemistry we have, and tells you how the material is processed, and how the materials, what the properties you have. That's what you have, right? That's typical data, property data sheet you have. Actually, most of the databases have today's like that. However, we know that from material science and engineering point of view, that's not really what we really study. We really study what's inside, structures. We study what microstructure is, right? Then we understand how these microstructures or the phases play different roles together, right? We try to start the green refinement. We try to take some different control of different metastable phases. Then we really want to make sure our green boundary is strong enough, very strong. Or we eliminate the green boundary altogether, like single crystal, like nickel-based single crystal materials. So that means if we want to design the materials, then we have to understand the connection between them. As I just showed before, we can do that, right? We can calculate the phase stability, that's the first thing. And then we can calculate the defects, right? We can calculate the property of different phases. Then we can see how the green size will affect our properties. Then we put them together, we can design. That we call a CALPHAD-based material design approach. Of course, that was not my invention, right? It's actually it started when CALPHAD was developed back in the 1960s. But I want to refer one paper to you because this kind of charts I think is very interesting. It's by Greg Olson. Sometimes now it's called the Olson chart. Greg Olson was at MIT as a student when a PhD student, when the developer of CALPHAD method, Larry Kaufman, developed it. And so he gained the knowledge very at the early days because Greg Olson and Larry Kaufman shared the same advisor at MIT called Morris Cohen. Morris Cohen is one of the giants in material science. And so this paper is very good because it get a very nice overview of how it works. Okay? So if you're interested in this one, I want to recommend you to another. So this is the key part. So we call it phases, distribution and interfaces. So that's the design part of it. So we have to design what the phases we want and how we distribute the phases and what phases we want and how the interface between different phases. Whether coherent, you know, the nickel-based value works well is because of coherence of the interface. Same thing as aluminum alloys. Okay, you got a coherent precipitates. There's the distributions and the phase interfaces. For example, you have taken the phase field simulation that controls the distributions. I want to refer you to two papers if you're interested in this topic. And again, Greg Olson wrote another paper in year 2000, 3 years later, his first paper. I called it Design a New Materials World. Again, talk about the history and so forth. But it works, a very nice paper. And then it was 2014, there's another paper by Greg Olson and Charlie Kuhlman. And Charlie Kuhlman was Greg's grad student at MIT, at Northwestern. And Charlie Kuhlman, and then we started a company called Questech. But 2014, Charlie left the Questech. Yeah, he left the Questech 2012, went to Apple. And in 2016, he went to Tesla and SpaceX. And 2016, he was hired to Tesla and SpaceX as the VP for both companies for materials engineering. And there are two people. Well, I heard there are two people working in both companies. One is Elon Musk. He's the president. He's the CEO for both companies. And Charlie Kuhlman is the second person and the vice president for both companies. So they talk about the material dynamics from CALPHAD to flight. Actually, the steels designed by Questech is now in that in the launch we had a few weeks ago to the International a space station. One of the steels designed by that company. Use the concept of this one. And you mentioned metagenomics. Of course, I want to mention about metagenome. And some of you know that I coined the name in 2004, inspired by the human genome and the CALPHAD approach. So this paper is a very nice paper to talk about how CALPHAD started with metagenome and to flight. Flight was, to the airplane, not to the spacecraft. Okay, so I'm going to show some examples of what we have done. And we did some work in industry we cannot talk about, but I want to show one example is that back in early 2000, and at that time people were trying to make the MGP, magnesium diboride, a thin film. Magnesium diboride was discovered as superconductor at that time. And everybody trying to make it. However, we know magnesium is very easy to get oxidized, has very high affinity with oxygen. So it's very difficult to make it. And the magnesium has very high vapor pressure too. So then we worked with, the physicist came to us, say, can we tell them how to make it? So we designed, we calculated the phase diagram. There's the pressure temperature phase diagram. And you can see that you can make the gas phase and the magnetic diboride stable. So this is the window we should process. So it depends on temperature. So you should adjust your pressure. That pressure, of course, is the magnesium vapor pressure. So it's very, very high. So it's almost impossible to control it by MBE or the PLD, laser pulse laser deposition. Okay. So then we work together to develop a method called hybrid CVD, because CVD can give a very high vapor pressure. So put a magnesium inside the chamber, and with the dipole ring, hydrogen comes in, then you form the film from here. So we made a very nice film. It's 100% pure of magnetic diboride without the oxygen, because oxygen is expelled already from the CVD process, and almost no defect in the making. So I've got a patent for that, work with a physicist at Penn State. That's one example. So design this one. And the second example we have is that to grow this multiferroic material, bismuth ferrite and bismuth magnetite. And this is the oxygen partial pressure and the temperature. Again, is a potential phase diagram. And this is from 10⁻⁹ to 10⁻3rd. So it's a very large window. It's 2 order magnitude. So everybody makes bismuth ferrite very easily. It's a very large window to make it. However, bismuth magnetite is so difficult. Remember, this is -9 to -3, right? This is -7 to -3. And the range here is half order magnitude. This is 2 order magnitude, half order magnitude. So it's very difficult to grow phase pure bismuth magnetite because the window is so small. Again, we work with Derek Schwann's group, and they do experiments, very nice, very beautiful experiments, beautiful read pattern, and then we do the calculation there. Of course, calculations always have uncertainties. The dashed line sort of gives the uncertainty range. But this uncertainty is still big enough, right? The window is still big, but this one is very big. This fluctuation will reduce the window by half. So it was very, very interesting work. So we made it. That's a very nice one. And lately we made an even more interesting one, is to grow a strong rusinate. And this diagram is so interesting. Look at the previous diagram. It's very straightforward, right? Straight line and so forth. But this one we found even more interesting that you cannot do that. You get 2 types of diagram here. So one goes this way, and another goes another way. This is from experiments, right? You see, experiments, you make 2 faces here, but here you make 1 face. So your Gibbs face was different. So Gibbs face above here is 4 minus P, and here's 5 minus P. So you have 1 more degree of freedom here. Why is that? So it took us to figure out. So actually you have very 2 different conditions here. This is like a closed system. This is like an open system. So this diagram combines the closed system and open system together. 2 diagrams actually, 2 different conditions. Why that happens? Because of the MBE process, if you increase the oxygen partial pressure high enough, you don't form this ruthenium solid anymore. Ruthenium solid is completely oxidized. So you change the condition completely. So we saw this diagram is very interesting. It's very useful for the MBE. We call it Tombe phase diagram. So some of the names are MBE phase diagram. That was published in 2018 because we found it so strange, right? So strange. But of course, the bottom line is because ruthenium, okay? Ruthenium solid is not stable anymore when the partial pressure goes at high, partial pressure oxygen goes at high. So the oxygen partial pressure is the partial pressure and total pressure and is very important concept when you deal with gas phase. So we learned a lot on this one. You see, it's interesting, right? Even after I worked so many years for thermodynamics, you still get new things to learn, because reality is very complex. Okay, then another very interesting topic we work is that we all know that green boundaries are not stable. Single crystal is more stable than polycrystal. We learn that all the time, right? Then single crystal is more stable because green boundary has a high energy. But it turns out that's not true. Because when the green size becomes so small, right, it becomes actually stable. Okay, so that's very interesting because we all know that green boundary has segregation, right? Because we know the elements can segregate the green boundary. But however, we never talk about whether that segregation reduce the green boundary energy or reduce the boundary energy of the system compared to single crystal. So it was in 1990s, because in 1990s, people started making nanomaterials. Then some people think it was German scientists that said, gee, if I make a green so small, and then you have enough segregation, actually the nano green is more stable than the single crystal. Oh, that was pretty interesting. Then many people started making that one because if it's not stable, it's a problem, right? You have nano green has very good properties. If you heat it up, it all grow very fast. Then you lose all the properties you need for nano that you made for nano greens. But turns out you couldn't make it stable. What it means is that, let's think about what happens. So if you have a polycrystal, you have material, you make a polycrystal, you have green boundary, right? But then you can do segregation. Now you have two internal processes happening at the same time. You have the green growth, right? That changes the green boundary area. Or you have a redistribution of the elements between the green and the green boundary. So it's actually two processes. But previously, we only talk about one process, green boundary change. But it's a two coupled process. If you do one, actually the friends will be different now, right? So suppose the fixed temperature, fixed pressure, fixed mass. So you only have the internal process. So you now have two processes. One is the change of the area. Another one is the distribution of the elements between the green boundary to the green interior. You have the distribution. So the internal change of the mass, they're all completely fixed, but you have internal change. So now what is intervention? What is the green boundary energy then? Green boundary energy will be the Gibbs energy of the system to the derivative to the area, right? So you do the Gibbs energy to the area with fixed temperature, fixed pressure, fixed overall composition. So you now do the derivative of this one, you get two terms. One is the intervention energy. Another one is this segregation, right? Segregation, of course, this has started before. That's called a Gibbs absorption. And this one also started before, that's green boundary energy. But we don't put them together. We started them separately. Okay, we started this Gibbs absorption. We started this green boundary energy. But if you put them together, the combination can make this one to be zero. Because this is positive, this could be negative, right? Negative. So that's what happened. You can next happens. So in 2014, a long time, we got some work with the Army Research Lab. They asked us to do this modeling. So we did this modeling. We take one alloy, binary alloy, iron zirconium, which is the did experiments. So you do different compositions, different zirconium concentration. So you have the stabilize the green side. That means the green boundary energy is zero, gamma is zero. That means no driving force for green growth anymore as a function of temperature. So the blue symbols here are the experiment data to X-ray at different temperature. And this is for different zirconium concentration. So the red one is 0.04. So that's the experimental composition, okay? Experimental composition, we did that calculation, is predicted thermodynamic stable nanogreen of iron zirconium bonding system. So it's pretty good, Of course, the model always have parameters, right? We need to do some dynamic modeling of the green boundary, we do some dynamic modeling of the greens, and this is the BCC phase. We had it already, right? We have it, but we need the green boundary modeling, okay? So that's do some work modeling there, we can predict it. That's and now I want to jump to the thing about the transport properties. Okay, now we talk about the transport properties, we use the phi, the free energy phi, which has temperature, stress, electrical field, and the magnetic field, mass, and internal degree of freedom. So we put all of them together here. Then we add the driving force, would be the first, we need to now put the three terms here. The first derivative, second derivative, and third derivative. Okay, so the first derivative is give us the driving force. So that means this is stable, this is stable, and this is unstable. This is all equilibrium because the derivative equals 0. But it's two stable, one unstable. So that's first term. Then second term talk about the stability. So second term here is all positive. It's positive, E2 positive, so it's stable. Then you got the inflection point. It's the limit of stability. Inside here, it's unstable. Okay, so D3 cannot be shown here. D3 basically means that all the first or third derivative equals 0. Okay, you cannot present this one directly. Okay, because you have to do that dimension to do that. Anyway, but one important concept is that when all of them equal 0, D, D2, and D3, driving force equals 0 is the limit of stability, and D3 that's what we call a critical point. I'm going to show one example of critical point. And then, because it's the internal parts transport, so you have the irreversible process, you can have entropy reduction. Entropy reduction could be many processes happening at the same time. For example, you could have the electric field and temperature field at the same time. Okay? And then we can talk about isothermal diffusion. So after diffusion, you have the mass, the d psi is the mass transport. The driving force is the negative gradient of the chemical potential. Thermoelectric property, so you have the transport is the electrons, okay? And then you have the electron potential, and the heat transport is entropy. The driving force is the temperature gradient. Heat transport is the mass and temperature, the mass and temperature gradient, heat transport. And there are many other ones. I want to go back to the table I showed before. This one, so I'm going to go back to this table. That table I showed before. So this is the property I'm going to mention. Okay, thermal transport, or the thermoelectric. But how about this one, right? Stress transport, electric migration. Electric migration actually is what happened in the solders. Okay, magnetic migration. But how about another ones, right? How about stress to temperature derivative? How about electric field to temperature derivative? How about a magnetic field to temperature derivative? Okay, so there's a lot of other quantities we can talk about here. Or how about the electric to stress derivative, right? That's all ferroelectric property. Okay, so a lot of other properties we have not explored yet. What does it mean? That means we look at this one again, because this is what we have talked about it before. So there's a lot more of it. Okay, of course, we're going to talk about the Seebeck coefficient only this time. Okay, I have some examples in a few minutes, I believe. I have about how many minutes I have left? 80 minutes. Okay, so to do this, so it looks very good, right? We do the modeling. So what's the challenge in the modeling? One of the challenges is like, is actually the strength of, so you see, everything has two sides. The strength of CALPHAD modeling at the same time is a challenge. We said we can do multi-component. That's one of the strengths of CALPHAD. But when we do multi-component, we start with pure elements, we go to binary, go to ternary, go to multi-component, right? However, if we change one component, for example, we change ion, then everything involved ion has to be changed, right? When I think about they have a 10 component system, 20 component system, how can you change that? Why? It's very difficult. Why is it difficult? Because when you do modeling, any type of modeling, right? You got your data. As soon as I got the data, you forget about the sources. We get the data, right? And then when you put data in the format, you forgot the metadata. Okay, when you got your database, you forgot the history of how the database is developed. And then when you got your database, everything to forget, right? So you want to revise the model, you have to go back to redo everything together. So that's almost, of course, is impossible. That's why it's very, very difficult to change your database, a bigger database, even today, any database. For example, if you do the molecular dynamics, right? You do a 3-component database, 3-component molecular dynamics simulation. You want to change one of the parameters, you have to do all the parameters together because all the parameters are correlated. It's very difficult. That's why it's so difficult to do the modeling. So that's one thing we did. We want to improve it. Another thing about sigma phase. I mentioned that paper. That sigma phase, they mentioned about 5 sublattices, but they only use 3 sublattices. You can see that the experiment has 1, 2, 3, 4, 5 sets of data, but the modeling only has 3 sets. That's 2018. Why? It's because it's complex. Because you got so many parameters to model. But however, if you take a DF data, it actually can predict the 4 sets reasonably well without any fitting parameter, complete prediction. Of course, now you need to improve the mix a little bit to make it better, right? Because this has no interaction parameters here. So to that one need new tools. I know that I'm not teaching thermodynamics anymore. I taught 15 years at Penn State. I wrote a book out of my teaching notes. So I encourage you to buy this book. Of course, I get some royalty too, but it's a really good book, I think. I wrote this one together with Professor Yuan, and he's a research professor in our department. We have been working together now for 17, 18 years now. And he's an expert in DFT calculation. He taught me all DFT calculations. So we need the tools, we need new tools. Also for any modeling, we need uncertainty quantification. To do that, we actually start to the program and a lot of open source codes, high throughput codes. And I'm not going to sequence how we did it, but now we have data generation, we have DFT data, we have the machine learning data. Machine learning is new code. We don't have it, we're developing it yet, we're still developing, but we do have one you can use if you want to try it, which can predict the formation energy of any compound. For example, if you get a compound, I don't know oxide yet. I don't know oxide yet. If you have a compound, you need energy, formation energy. Take this code, put your structure into it, it will predict the formation energy for you at 0 Kelvin. Basically dead H. Well, dead H doesn't change with the temperature much, okay? So it gives you dead H, so to speak. So we can try this one, this new network. And the accuracy, I think, is like a 40 MeV so far. So it's 4 kilojoule. So it's not too bad. It's probably comparable with the calorimetry measurements. And then we also have DFT case with high throughput DFT calculations. If you want to do some DFT calculations, and you can temperature dependent with Debye model or Formal model, you can get its code. It's again on this website. And when you have to get the code into the modeling, right? So we have the data processing, we call it. So we got a CALPHAD that's developed by Richard Otis, one of my former students. He's now at the JPL. And he also developed, started SBay. SBay now is being developed by Brandon. If you can go to the 2 websites, it's one stroke to install on your computer. Okay, you can go to SBay, you will install PyCAF at the same time, I believe. Or otherwise do two installations. And then to the uncertainty quantification, we work with the people or scientists at the Oregon National Lab. They develop another code. It's also open source called the uncertainty quantification. You can do the uncertainty quantification different properties. And of course, it's open source. So if you are so keen to do some development for your own use, for example, you may want to develop your atomic potential for your MD simulation. Well, you can take this approach and maybe do a program to do the modeling of whatever you do, whatever model you have. Okay, you can do the properties. And so this one basically I want to mention about the data ecosystem. So the machine learning, you develop the data, then the DFT. So machine learning now is the most efficient produce data, but you need to input the data, right? So you can do DFT data or Abelian modeling dynamics to confirm those data or generate data for the modeling, machine modeling. Then goes to the FEM, which we are working on too, to predict mechanical properties. And then you experiment the validation of the properties. So in that case, I will call it called a proto data. Proto is original data for machine learning, DFT, MD, and the FEM and experiment. And from this data, you process them, you get a process data. Then from the process, they can do material design including the chemistry and the processing. They can manufacture the materials. They can use the materials. And during this manufacturing process and the material surface process, generate new data. So your new data gets into the proto data and recycle it to the process data. Then you can read to the process again because you get a better data now, right? You get better design and a better service. And at the end, the materials has to be recycled. They recycle new data there, okay? The new data will go to the produce data and then refine your process data. You get new knowledge because the space is so big, right? So you get new data, you can refine. So we hope this continuous process, which is we call the data ecosystem. And also I asked Patty at our college to construct a more informative diagram, the ecosystem. So we hopefully that the different data sets from your DFT or somebody else's DFT or experiments or some secret data from the industry and or from some data from remote somewhere you got from the ancient time ago, and all come together. They collect I call it ocean of data. So it's not data ocean, it's ocean of data. It did come together to form an ocean. Then this ocean, we can process data, right? From new life, okay? We hope the SBA will help us do that. And then the data will be used again by people like you to do more calculations, to more design and more processing and new data and recycle again. So we hope our tools, open source tools can create this data infrastructure and to have this reuse of data and put all the data together. So we would love to work with you. Well, I know that if some of you become scientists and engineers and become professors, and I hope you take this tool forward, we work together to build up this data ecosystem for materials. Or actually it can go beyond materials, right? Because DNA is material. We actually were talking about with the polymers. We hope the polymer can take this approach too. And also the polymer can do it. Okay, with that, I'm now 11:31. I want to tell you that in the fall, I'm going to offer the materials of Mathsci 580 called the Computational Thermodynamics. It's a fall in even years, so 2020, we're going to have it. And that one is talking about the thermodynamic modeling, how we do the modeling, right? How do we, of course, there'll be new things added this year is machine learning, will be part of it. We didn't have it before. We had DFT before, but we don't have machine learning. And then every other year, I teach the computational materials science on the continuum mesoscale simulation, which including the phase transformation simulation from the 0 dimension, 1 dimension, 2 dimension, and to 3 dimension simulation of the microstructures. And I also want to mention that I have an overview paper, which it's peer reviewed. It's reviewed and submitted back to academic material. It's called Computational Thermodynamics and its applications. I hope you can get accepted very soon. And in the cover, everything I talk about here. But something I did not talk today is because of time limit is I want to just show you here very quickly with all the slides I prepared. It's on the mechanical properties. Okay, we did a lot of mechanical property modeling. We did elastic property, dislocation property, stress strain curve, and hardness modeling. Okay, so this is all through the energy, okay? So I'm gonna talk about them now. And then I have another one is the tools, okay? The tools is very important, right? We have details about tools, but we cannot go through them here. Is that I hope I will go through some of them at the meeting at the class in 2014, in the fall. Is that 2020 in the fall is talk about this modeling, experiment data modeling, and the first principle modeling, and the statistical modeling, and now machine learning into the framework, and then there's a prediction of the properties. So of course, this cycle, I think, is very important. It's iteration, because every time we do a calculation, every time we do experiment, we get more data, I get a better understanding, and we do the iteration. So that's why this data ecosystem is very important. We have to have a mechanism to store all the knowledge, store all the data, so we can better and better, not repeat what we did before. All right, with that one, I stop my presentation here, lecture here. If you have any questions, just let me know. Ask the question. You can even either unmute it or write it in the notes in the chat, and we can go from there. All right, thank you for your listening. And any questions from you guys?
Hi, Dr.
Yes. Hey,
yeah, it's I also still learn new things. I just still like has some understanding, like not very well understanding about those CASI. So when you mentioned in the very beginning of the slides, so those CASI, we can actually consider them, because we also have like compositions, like the temperature and the pressure already. And those CASI can be this variable. And in the meanwhile, as you mentioned, it can be like an internal state. It can also be like a function of those variable, right? Like
That's
you
right.
can actually, for example, if we talk about the order disorder transition, then your CASI can be those like side fractions instead of composition, right?
That's right.
Like then
exactly.
you drive into like, for example, you have order disorder transition, you're driving from like a non-equilibrium to the equilibrium, you try starting from the disorder system and transform to an order system. And then CASI become like side fractions.
That's right. Because that could be a fraction of the phases too.
Okay, yeah, then that will give you like all degree of freedoms to really think about your this non-equilibrium, equilibrium, also metal like local equilibrium, those transitions.
That's right. That's right. That's right. That's why I can do the homogeneous system.
Okay.
You can have distribution too.
Yeah, I think that
right, the temperature cannot be internal variable because the internal variable must be the molar quantity.
Okay.
So
it has to be the molar quantity.
The potential would be driving force for that molar quantity. So the potential, the temperature would be the D.
Okay. Yeah. Now I understand that. Yeah. Great. Right. Thank you.
So actually, we keep learning, right? For example, I mentioned the Seebeck coefficient. We did that one because we got a project from NASA, JPL, asked us to study some electric properties. Then we found gee, so why people predict the way they do? We found that we can improve it. Same for diffusivity, right? About 10 years ago, all the diffusivity prediction was by MD simulation because prefactor. They calculate the barrier to the prefactor by the MD. Right. And then we found that, we can do better. We can actually predict the prefactor also by the energy.
And then from the derivatives.
That's right, from the derivative. Exactly. Yeah. So that means that, of course, kinetics will be different from thermodynamics, right? Because it has time involved. Thermodynamics has no time involved. So any properties with not time in it basically can be predicted by the energy.
Okay. Right.
And then you have to do time evolution, then you have to do the simulation. Then now by the MD simulation, the phase field simulation, and texture simulations too.
Yeah. And also this TC Prisma, you can also have time evolve of the nucleations. Yeah.
That's right. Yeah. That's right. Yeah, then you have statistical mechanics there. That's the uncertainty, right? You have statistics. Right. Yeah, statistics is very, very important. When I talk about the critical point we predict, it's based on statistical mechanics. So you have this typically top of thermodynamics. We have the classical thermodynamics. We have statistical thermodynamics. We have the irreversible thermodynamics. Actually, they're all the same thermodynamics.
Connect all together.
That's right. It's all together. Because statistical thermodynamics is about entropy.
Right, partition function.
Irreversible thermodynamics is about the energy, not an equilibrium. So, in my opinion, it's just, of course, it's difficult to get these functions, right? Because at the unstable state, you cannot calculate entropy because entropy diverges. So you have to have a way to calculate the entropy at the unstable state. That's where you have to use statistical thermodynamics.
Right. Okay, thank you very much.
All right, any other questions from people? I saw two comments, I saw two chats. One is about where I share the slides. Yes, I think I'm going to share the slides, including this one, did not present. And another question is that will I be teaching simulcalc in the fall? Yes, we will do that. In the fall, we can teach simulcalc. And another fall, in the 581, we're going to teach Dijkstra, phase field, teach Prisma, and that's all. And also the called the TTD diagram calculation. That's in the 581. That's next fall. And in the fall, this 580, this fall, in addition to simulcalc, we're also going to teach about CALPHAD and aspect. Okay. So that was a new tool we developed, which can use for database development and also for the open source. People can develop it further with their own model. Because CALPHAD has a very unique feature is that you can do your own model. Okay, all the commercial code the models are hard-coded. You cannot change any model there. You can only use the models available in the software tools. But in CALPHAD, you can do your own model. That we think is one of the major strengths this open source code we have. Of course, our code is relatively young, and so it's still improving all the time. We have still meetings with Richard to improve it. Every 3 weeks, I believe, we still discuss the improvements. It's continually improving, and we're also going to put it on the supercomputers, and they can do supercomputers, multi-process calculations. All right, if there's no more questions, and it's now 11:40. All right, so thank you all for attending the lecture, and wish you all the best in your graduate study, and have a good time at Penn State.